Happy Wednesday. It's great to have you join us. Welcome to Passive House Accelerator Live, where we explore how to slash the greenhouse gas emissions from our buildings and to make them more resilient to the impacts of climate change. My name is Zach Semke. I am a host of the Reimagine Buildings Collective and director of Passive House Accelerator. And I'm super excited today to be welcoming Ryan Abendroth for this special masterclass series of Passive House Accelerator Live focused on ventilation flow impacts on equipment and building performance. This masterclass series that happens once a month in the Passive House Accelerator Live sequence features presentations by experts in residence from the Reimagine Buildings Collective. And the Reimagine Buildings Collective is our membership community where we bring together practitioners who are working on passive house and low embodied carbon and natural materials, and we bring everyone together to support one another in the leaps that we're all making in our work. And so you have access to peers who are on the same path that you are, as well as access to experts like Ryan. And so on Friday, we'll be doing a follow-up Ask Me Anything session with Ryan to dive deeper into all of this. So after, we'll be able to get to some questions today. And if you have more questions and want to dive deeper, and you're not yet a member of the collective, we encourage you to join us. It's a lot of fun and some really great information and connections with people like Ryan. So speaking of Ryan, very excited to introduce him. Ryan is co-founder of Build Zero Consulting. He's also a certified passive house consultant. Since 2009, he's dedicated his career to advancing low and zero energy buildings and expanding the impact of the passive house movement across the US. A former certification manager and longtime instructor for PHIUS+, Ryan has helped shape national passive house standards, including contributions to the PHIUS+2015 Standard. He's also a senior lecturer at Washington University in St. Louis, where he teaches design studios and seminars on zero energy building practices. With experience spanning multiple climates and project types, Ryan has guided some of the first PHIUS certified projects in Kansas, Indiana, Missouri, and New Mexico. And he is just a fount of awesome information. So Ryan, please take it away from here.
All right, thank you for the introduction here. So we're just gonna hopefully pause 1 minute, and here we go. So we're going to talk about ventilation today, and this strongly shapes the sort of amount of energy use in the building, but also all kinds of other impacts of the building. And so as we go through today, we're going to look at what ventilation rates are commonly used in passive buildings, explain how changes in airflow affect energy recovery, fan power, and therefore heating and cooling demands and loads. Think about like sizing the equipment and then interpret some of the results. So we're going to look at 4 different kind of building typologies and see how some of these things play out in those different project types. So I'm going to make some basic assumptions. I looked at some of the names, in the chat here, and most of you are probably pretty familiar with passive house and ventilation, or maybe watched some of the other passive house accelerator meetups over the last, month or so, because there's been some basics on ventilation and things. So we're going to assume that you know a little bit. We're also going to assume we're building airtight buildings for the most part that require fresh air ventilation, that we're going to be, exhausting from the kitchens and bathrooms and supplying to living spaces and bedrooms, that we're going to have ERVs that recover latent and sensible energy, or HRVs that are only sensible. We're going to assume that heat recovery occurs when air streams pass by each other in a heat exchanger core or heat recovery core, and then that the fans on the ventilation equipment produce waste heat. And then we're also going to talk a little bit about how there's multiple data sources that exist where we can get information on efficiencies of various pieces of equipment and how that impacts some of the projects. So with that, we're going to look at a few example building typologies. I just put a few quick snapshots up here. It's not really all that important, but just so you know where I'm getting my data from, it's sort of from these four project types: a small single family affordable project, a larger single family project, much larger multifamily that's having decentralized or unitized ERVs in it, and then a multifamily with a centralized ERV. So when we talk about the ventilation rates in passive buildings, there's a bunch of different ways that we could look at it. You probably need to meet local code. There's ASHRAE requirements, 62.2, 62.1. There's Energy Star. There's a zero energy ready home. Then there's PHIUS or PHI recommendations. And some of these work together fairly well, and others maybe don't so much. And we're going to talk about that very briefly here to sort of set the stage. But just a quick example, if we were to like just take a very simple single family home and kind of dumb it down a little bit, we're going to get much smaller airflow rates, maybe 50 CFM minimum, 100 CFM, up to 100 or 200, maybe even more than that when we look at large single family homes. And this is kind of a simple equation, but it's about the floor area and the number of bedrooms to give us the CFM rate. And I just want to point that out there because there are a lot of engineers that are going to be doing different calculations and sizing based on these various standards. When we look at kind of passive building or potentially PHIUS or PHI certified projects, especially the PHIUS ones, they need to meet Energy Star certification criteria. And so I just cut out a few pieces in the Energy Star multifamily new construction checklist here, where when we specifically look at the kitchen exhaust airflow rate, for continuous ventilation, it says greater than 5 ACH based on kitchen volume. And this is a really kind of big thing to understand because that 5 air changes per hour ends up being very massive on even the smallest of kitchens. So that large multifamily decentralized building we just looked at, those are kind of kitchenettes or pretty small kitchens. And still, based on 5 ACH, we're looking at roughly maybe 60 CFM required for that kitchen exhaust. And it's worth kind of referring back to this previous slide that that is the entire ventilation rate required by ASHRAE 62.2 on a kind of continuous basis, just based on the local exhaust requirements. So there are other ways of dealing with that, but for now, we're just gonna kind of say that or make an assumption that that's going to be a lot of airflow. Now, if we look at the footnotes that are referenced here, and I am showing footnote 76 in this document, about halfway down, it says, as an alternative to item 8.1, dwelling units are permitted to use a continuous kitchen exhaust rate of 25 CFM per this table if they are either a PHIUS or PHA certified. And we can sort of, stop there. You can read the rest of it. But it's worth noting that if you're getting a PHIUS certification, you can use 25 CFM for the continuous exhaust rate in the kitchen rather than that 5 ACH. And that's generally a quite significant savings. So we'll put that on the back burner for a second and, just briefly talk about the engineer versus CPHC. And I think this is like at the root of what we're really going to talk about is that, an engineer wants certain things, like not to be called back because there's comfort or indoor air quality concerns. They want to make sure that they're meeting all their legal requirements, codes and regulations. Again, because if there's problems, they can say, hey, we did it, correctly per the guidelines. Also, I'm seeing this a lot too, where they want to get through the building department approval, which again is probably based on one of those other guidelines that we mentioned earlier. What they're not necessarily interested in is passive building certification compliance or energy savings. Tangentially, maybe they are, but I think that's a secondary kind of concern to some of these at the beginning. So what we often or might see is higher airflow rates, um, just to make sure that you're meeting all the requirements, you're getting through the building department approval and those sorts of things. But the kind of higher or conservative airflow rates we'll see coming up do come back to maybe cause some problems on meeting certification targets or energy savings. So we're going to talk a lot about optimizing ventilation system specifications and why optimize? Well, in many cases, the efficiency of the ventilation system can have a large impact on building performance. We're going to quantify that on the next slide. And then the other thing is upgrading a ventilation system may be as simple as swapping one piece of equipment for another, especially on like a single family, pretty straightforward project. If you can just uninstall one ERV, and then reinstall a new one, perhaps digitally, and so you install the right one the first time, you can have this really outsized impact on the building performance without changing the thermal envelope or having to redraw it if you're working on a PHIUS certification and re-import the model and all that stuff. It can be really significant to just change a number in the model, change a piece of equipment, and make a big impact. So in our large single family example, just to kind of put into the impact here, and I highlighted the wrong thing here, but if we just look at the sensible recovery efficiency, if we have a very high, maybe the highest, best system out there at 86% sensible recovery efficiency, and then we drop that down to 70% sensible recovery efficiency, and we look at the results coming out of Woofy in this case, we have a heating demand that goes from 5.49 kBTUs per square foot up to 6.56 kBTUs per square foot. So that's, something like, I don't know, 18% increase in heating demand. It's quite significant when you're trying to meet some of these criteria for certification. So we'll just kind of keep that in mind as we go through it. So what does optimizing even mean? To me, it's increasing performance on paper to better comply with energy modeling and VS requirements. That's one part of it. Honestly, I'm more interested though in the increasing of the real world performance of the system. And it's important to remember that these systems are running 24/7, 365 for the lifetime of the equipment, or, probably not the building. But it's a really, all the time type of load that is happening to that equipment and building. So when we look at these factors for optimizing the performance, the first thing we can do is just move less air. So if we have the same size heat exchanger and we move less air, we're going to have a just better outcome. So that's going to result in less fan energy, which might mean that there's a different internal heat gain impact if it's inside the thermal envelope. This lowers energy use just in general. And then also benefits to the longer life, potentially, of these pieces of equipment because they're running at a lower, slower, easier speed. The other impact might be the lower source energy. The higher efficiency, though, is the biggest impact that's happening here. So if the size of the heat exchanger is held constant and air moves, there's less air, so air moves much slower through that core, then the heat transfer between the air streams increases, right? The slower they pass by each other, the higher the transfer rate. Alternatively, we could keep the same airflow, but increase the size of the heat exchanger. it has the same effect. Same airflow, bigger heat exchanger core, the air is going to move slower through it, and then there's going to be higher transfer rates from one airstream to the other. When we talk about data, PHIUS likes to use the HVI data, and it's very useful for a few reasons to use that data. And we're going to go through a lot of examples here. But the data that you can get out of HVI is at multiple airflow rates. So the example here is a Renew Air EV Premium L model. And when we look at the kind of net outdoor airflow, we can see it starts at 59 CFM, it goes up to 121, 201, 227, and that's all heating, and then there's also one line for cooling. But with the airflow increases, we can see how that affects the other pieces of data here. So as airflow increases, power consumption goes up, right? The fans are working harder. They're trying to jam more and more airflow through the machine or through the heat exchanger core. And so the fan power is going to go up. The other thing that's happening is the air is moving a lot faster, right? So if we go from 59 to 121 CFM, we've like doubled the CFM. So we're doubling the airspeed through the core. And what you can see in terms of the apparent sensible recovery efficiency, or ASRE, is we're getting a reduction from 90% recovery efficiency down to 83% recovery efficiency because the air is moving faster through the core. Same with this next column over to the right, NMT, net moisture transfer. We have a 77% transfer rate down to a 0.69 or 69% transfer rate. These are actually really quite big drops, right? Running this system at 60 CFM versus, let's even go to 200 CFM, is a 13%, difference in the sensible recovery efficiency on your, ASRE. So pretty large differences. We're going to actually show like impacts on buildings here in a minute. But want to point out that sometimes these are not small, right? Renew Air also has not just a premium L, but an S and an M, and now they have an XL. And we can sort of compare some of these between the two. Like, let's just take the premium M here at 51 CFM. We can compare that to the premium S at 51 CFM. So that's the first, kind of row on each of those entries. And see that that same 51 CFM, the power is higher in the smaller unit. Again, it's trying to move more air through a smaller heat exchanger core. And therefore, the sensible recovery efficiency is 77 rather than the 84 as apparent sensible recovery efficiency for the premium M. Okay, so there are quite a few differences. And of course, it gets like much different on the sort of extreme. If we want to like even increase the ASRE further from 77 to 84 all the way up to 90, right? We can use the EV Premium L to do that at roughly the same, flow rates. It's even kind of more so if we were to take the small and bump it to close to its maximum at 102 CFM. Kind of follow that row across, and we see that the power is 78 watts and the apparent sensible recovery efficiency is 71%. For that same 102, we could just use in the premium L the 121 CFM. So even more, but we see that the wattage is 37, so it's less than half the amount of watts used. And also it's 12% higher from 71 to 83% apparent sensible recovery efficiency. So I know there's a lot of numbers on this and it might be kind of tricky to follow, but I think the main takeaway is smaller systems for the same airflow are going to use more power and have lower recovery efficiencies. And larger systems are going to be more efficient, run slower, and have higher recovery efficiencies. And to give you a sense of the difference between these and just like their sizes, you can see the EV Premium S here, all the way up to the X, and they're roughly about the same size boxes. There are some differences, but the one difference is the width here. So we have 9.5 inches versus 12.5 for the Premium N, and by the time you get to the L, it's 23.5. So the heat exchanger core ends up being much larger in that Premium L. Okay, we kind of looked over that again. The other thing that is, I just want to point out that's very typical is the ERVs versus the HRVs. An ERV, as already mentioned, is recovering both moisture and the sensible recovery temperature. And so the thing to just point out on that, if we're looking at like the Zender here, is that because the heat exchanger core is allowing moisture to move through that membrane, it generally won't be as conductive as a material that might not allow moisture through it. I think like a simple example is you think of like a metal plate. It's highly conductive. It allows a lot of heat transfer through that compared to some composite material that's going to allow both heat and moisture through it, which maybe isn't as conductive. And so you'll just see this across the board that HRVs are generally, I don't know, 7 to 10% more efficient than their ERV counterparts in the same product line. And you can kind of see that here from Zender. So that's sort of just a side note. We also have different data looking again at this ERV, HRV, Q450 from Zender, but this time at the PHI data. And we can see the ERV is 83% efficient, the HRV is 88% efficient. And if I was to just, drop back to this, it's kind of interesting that those are the numbers given the HVI data, because it's showing that from PHI, the ERV is less efficient when we look at HVI data, because it was 83% on the PHI data. Where if we look at the HRV, it was 88%. So it's kind of lower. But still, you're seeing that same spread. I mentioned earlier, like I like the HVI data mainly because it has these various levels, whereas the PHI data is just kind of one number. So it's generally, you could use either data, but depends of like how far off you are from the standard airflow rate of that unit, will have an impact on what your overall heat recovery is. And then just to compare, like, hey, this isn't just a Zender thing. Here's the Brink Flare ERV on the left, HRV on the right, and you see a 5% difference in those two pieces. Okay. We will see the same thing here in small commercial units. So this is a RenewAir HE07, and I've listed here summer, winter at the high, medium, and low flow rates for this project or this unit. And this is data direct from the manufacturer, which I think is something to mention. As soon as you get out of like HVI, I didn't even mention it's the Home Ventilation Institute. You can go look everything up on their website. It's publicly available, all these numbers that I've been showing from there. They, though, do not have like anything above maybe 300-ish CFM. So as soon as you get to that point, it sort of switches to commercial type units, and AHRI is the kind of certification body there, but they don't necessarily certify data, but they certify software and cores. So you may need or likely will need to rely on the manufacturer to put in the project data, what the temperature, differences are inside and out, to actually calculate this information. And so anytime you have one of those larger ERVs, you're probably requiring a project-specific calculation based on some AHRI standard process. In this case, we have a flow rate of 470 CFM on the left, the high one, and the sensible recovery efficiency is 70.8. And if we did the total recovery efficiency, or moisture recovery, if we are down at 53.3. And if we just reduce that down to 325 CFM, so again, less airflow, slower, more heat transfer, we see that sensible percent jump up to almost 76%. And reduce the flow further, we see that jump up to 79.4%. All right, so let's look at the small single family first. So this is a 1,200 square foot, 3-bedroom, super affordable house for an affordable program in Kansas City. And they ended up installing a Panasonic right here. So it's the 100 CFM version of the Panasonic, like IntelliBalance, I think. So when we look at that, we can see, again, same things we've been looking at. When it's at 53 CFM, we have apparent sensible recovery efficiency up at 83. As we move to 85 CFM, that drops down to 77. So that kind of 6% difference there. And we see it also in the moisture rates. This project originally was designed with a Brone, one of the Brone units that is much larger, more like a 200 CFM max unit rather than a 100 CFM max unit. And if we were to look at that same, like roughly 80, so we're comparing 81 CFM for the Brone versus 85 CFM for the Panasonic, we can see that that Brone has a bit more well, a couple things. One, if we look at power consumption, the Brone is about half the power that the Panasonic is using. So if we're just looking at watts used. The other thing is it's 4% more efficient or 5% more efficient, give or take, at the same flow rate. Although there is a trade-off there. It has a little less heat or less moisture recovery than the Panasonic. So I just want to point out here, though, if you're optimizing a building based on an 81% or an 83%, and your efficiency is actually 77%, then you run into some trouble here when going to actually design or certify the building. What we did was even a little bit worse. So the airflow in this project was at 90 CFM, and maybe even should have been a little bit higher. So this is a well undersized ERV for this size of project. Typically, you want to look at running your ERV at maybe 50% or less of its max capacity. I'm a big fan of 40 to 50%, or yeah, maybe 40 is being closer to the right number. In this case, we're running at like 90% of what the maximum capacity would be in this project. And that has a big impact on that sensible recovery efficiency by putting it down at 0.71. And I'll mention how I got there in a minute. If we just were assuming a larger ERV, right, something that could run even at 81%, which is, great or good, but not like super spectacular. Look at the difference in the heating demand in this case. We go from a 9.59 kBTUs down to 8.66. So again, like a full kBTU of energy use in this project for the heating demand just by increasing that sensible recovery efficiency, simply by maybe in this case, switching from a Panasonic or 100 CFM unit to something that's more like 200. And I don't want to say like the Panasonics are bad or anything, right? Like if you were running this at 50 CFM and that was your target, then you're up at 83% for that sensible recovery efficiency, which would do the same thing here. It would look great, right? It's just this project needed 90 CFM, which is pushing the Panasonic really further than it should be pushed. Okay. There is one other little side note on this is that PHIUS has developed this calculator, and this is the example for the EV Premium X. They're still working on this a little bit, so I don't know if it's public. I couldn't find it publicly, but it gives you the ability to put in the data from HVI. So you can see in this case, like HVI rated this at 102 CFM, at 197 CFM, at 244 CFM. And because of that, we're getting down to a, then you can put your actual airflow in there and it will calculate what your efficiency is. So in this case, if we were running it at 300 CFM, that's beyond, what HVI has just published in terms of ratings. And this will calculate kind of that curve continuing and show you what the actual effectiveness is for any CFM that you enter. So I think this is pretty cool. Like I said, I don't know that it's public yet, so maybe we're putting PHIUS on notice that they need to finish it up and make it public. But I mentioned that because that's how we got this pretty low 0.71 efficiency out of the Panasonic, was because we were pushing it past the rated HVI value, right? So we have a kind of curve that extrapolated that number for us. All right. One other last kind of point in the single family. This is just a different project that had this Renew Air EV Premium S specified. And I did a calculation looking at the Premium S and the Premium M and saw that the difference was approximately $37 per year, or 251 kilowatt hours per year at 15 cents per kilowatt hour as modeled in WFE. It's not a huge difference, but the price between those units at an online retailer was also pretty small, 1325 versus 1095, and it led to a payback period of about 6.2 years. So this is just going up from the S to the M. There is a cost associated with that, but this shows that the payback period is pretty reasonable. Actually, 6.2 years. You would hope that your ERV is lasting longer than that. And along the way, you get all these other benefits besides the energy performance. But maybe it makes it easier to meet your PHIUS criteria. Maybe it allows you some flexibility to dial down other, things such as the assembly or envelope. The incoming air temperature, because you have higher heat recovery efficiencies, will be a little bit warmer in the winter, so you'll have less thermal drift. And I think a big one here is you should get longer use out of your equipment because it's running at a smaller speed. There's less waste heat, which is, a whole nother discussion, and generally is just a better, slower thing. Noise, acoustics also usually less when the airflow is moving slower through the heat exchanger core. In large single family, I'll keep this one quick, but sometimes you are like, should I have one ERV or two or maybe more? And so this a project that needs like 219 in this case CFM. Should you use like this CA or CAQ 600 from Zender? And you can see that on the bottom where the CFM rate is maybe higher. Or should you split that and use two maybe CA 450s and get significantly lower fan energy because you're dividing that flow rate in two. And I think in this case, that's, if we just were to use this example, that's what we would look at. Even if we were thinking about it in terms of just using the CA 450, should there be one or two of them? We can see at the first one, if we split the airflow in half and use the lower value here of 123, we get an 82% apparent sensible recovery efficiency. If we go up to the 237 number here, which is not in one of the boxes, you end up with an ASRE of 76. So again, it's a 6% reduction um, from one ERV kind of maxing out its flow rate versus, two ERVs running on the lower side of what they want to handle. All right, let's look at some multifamily buildings first. So this is a quick kind of aside that the flow rate can matter a lot in multifamily buildings. Small changes in units can have big impacts over the building. And so we've seen this like happen before as we reduce airflow rates. Even if we don't change the apparent sensible recovery efficiency, the fact that we just have less air being moved, less makeup heat that we have to introduce into the building, gives us pretty large benefits. So we can look at our heating demand at the top here. It's pretty tight on the certification criteria, same with the heating load. If we're able to reduce our flow rates, we can get that down and kind of remain in a buffer on our PHIUS criteria. Another concept in this multifamily project is whether it's inside or outside of the thermal envelope. And when you have an ERV that's inside of the thermal envelope, that fan energy, and that is partially in the building, right? At least the way Woofy calculates it. And so you're getting a benefit on your heating demand by having it inside the thermal envelope. It is also increasing your cooling demand. And in this case, inside the thermal envelope, has a little bit additional source energy required. So it's worth noting that the cooling is going up faster than the heating is going down. And that removing this ERV outside of the thermal envelope reduces that cooling demand and load and reduces the total source energy. This does change depending, maybe a little bit anyway, depending on the type of project. So in a smaller decentralized multifamily, we're seeing some of the same things. And I want to point out, I did take a shortcut on this slide. So the heating demand is kind of messed up. And that's because when I flipped this ERV from inside to outside, it didn't change like the length of the ducts associated with them, right? So some of those ducts are running outside now. So don't worry about the heating demand. That's why it's a little funny. But if we look at the cooling load, when that ERV is inside the envelope, this project is over on the cooling load. And for those of you that have tried to optimize multifamily building in Woofy for cooling load, you'll know that it's pretty hard to, sometimes anyway, to make that change and lower that load. Like you have to have pretty significant shading or other things maybe, or lots of investment in the envelope to make any noticeable difference there. So just by taking that ERV and putting it outside of the thermal envelope, we've taken that fan energy outside and reduced the cooling load into the certification range. So again, it doesn't look like it's a huge difference, and on a yearly basis, it's 70 kilowatts a person. But to get within the PHIUS certification range, it's quite important to have this option to put this outside of the thermal envelope, essentially on the roof, right? All right, when we go back to the large decentralized multifamily, and this was one of the kind of genesis for the whole presentation here, and this is like the last big example. The engineer originally designed this as a project with each unit receiving or having its own ERV that has 85 CFM supply and exhaust. So typically these are one bathroom, one kitchen, small kitchen sort of units. And they assumed that they would not just use 20 CFM exhaust, which is the required amount for the bathroom, but they'd give themselves some leeway up to 25 CFM. And then using that 5 air changes per hour for a kitchen, they came up with, yeah, most of our units are going to be 60 CFM. So they go 25 for a bathroom, 60 for a kitchen, we get 85 per unit. The other thing to note on this is that this project has, I don't know, almost an infinite amount of different units. So there's 280 plus units overall, and I bet there's 40 or 50 different actual unit configurations, maybe more. So there are some setbacks, there's different plans, and most of these are practically custom. And so I think that was the other thing the engineer was thinking, like, I don't want to recalculate this 50 times. If I can just like choose the bigger unit and make it work there, it will work for, all these other units in the project. So every unit has this 85 CFM. There are also some other ERVs here, and I just took a quick screenshot out of the Woofy software to show you like there are some additional flows, but most of it is units. Some of these other ERVs are corridors or amenity spaces, etc. And what we're seeing is just reducing that 85 CFM down to 60 CFM per unit. Um, Gives you quite substantial, reduction again. In this case, I mean, we were finagling some of the numbers maybe a little unfairly, but it goes from not passing certification on the heating demand to meeting the certification targets. But you can also see it's a pretty decent reduction. It's also, if we were to just look at the source energy, like a 300 kilowatt hour per person per year target, which is, not necessarily insignificant either. The thing is, 60 CFM is sort of a compromise because if we were really looking at it as the absolute minimum that we could achieve for the project, it would be 45 CFM, 20 for the bathroom and 25 for the kitchen per that Energy Star exception in footnote 76 that I showed near the beginning of the presentation. And if we were to do that, it reduces, total airflow even further. And now we're looking at 450 kilowatt hours a person per difference and, a really quite significant heating demand and heating load sort of difference. There's also some minimal, cooling benefits as well. But the bottom, uh, you know, results look a lot better from a certification perspective and being able to meet those targets than the top does. And again, this is changing nothing in the building, no thermal envelope differences. It's just switching out the equipment. And this is actually the equipment that's being used. And I highlighted all these spaces in between these numbers because that's really what we're talking about, whether it's 85, 60, or 45. But you can kind of get a sense of when I look at the ASRE, there's going to be a difference too. If we're running this at 85, then it should be somewhere around 77 for the apparent sensible recovery efficiency. If we're running it at 60, it should be somewhere around like 81 for the apparent sensible recovery efficiency. So if I just compared 85, assume it's an SRE of 75%, compared to 60 CFM at 81%, these numbers get even better. If I go back a few slides, we went from 5.4 to 4.59. Well, when we factor in the recovery efficiency increasing to 81%, we don't just go from 5.4 heating demand to 4.59, but all the way down to 4.1. So we get another half a kBTU on our heating demand because the recovery efficiency is also going up. And to keep this simple, I left fan energy and moisture transfer the same. But it's worth noting that these two things are combined. Less airflow, less overall, heating need, but also less, airflow means higher sensible recovery efficiencies. So you're getting more heat transfer, less heat losses that way too. And if we push this a little bit more, I mean, just to, again, do that comparison between the 4.59 and the 4.1, Um, we can push it even more. And so what does it take to overcome poor ventilation system design? And before I go into this, one reason I chose 60 CFM, not 45, is the engineer was saying on some of the larger units that have multiple bedrooms, we actually will need more airflow for the supply side. And so I think it's more reasonable that we're not going to get down to 45 CFM, that we're going to be closer to 60 CFM for each of these units. And also, I don't mind bumping the bathrooms from 20 to 25 CFM because I think it's going to make balancing these systems easier, rather than trying to meet a minimum. If it measures out at 23, you're still good. So just keeping that in mind a little bit, I chose to go with the 60 CFM. Um, this is a pretty big difference. We've seen this on the last slide. So what does it take in the envelope to overcome this? I changed the roof R value, which was already kind of low, but from 28 up to 48. I added 2 inches of continuous insulation in the wall to take the R value from 26 to 33. And I insulated what was previously an uninsulated cellar or basement slab, up to 2 inches of, R8. Then I also had to take the U value of the windows from a 0.22 to a 0.18. And here's the results of that. We're still not down to the 4.1 kBTUs on the heating demand that we were just by switching out that ventilation flow rate. So hopefully you kind of can see how important it is to have a very accurately dialed in ventilation rate and then properly choose the ERV that's going to be able to provide that at a pretty high efficiency, low fan power sort of situation. Because in this case, swapping that out, which includes changing nothing, just lowering the flow rate or dial on these ERVs, is the same as adding R20 to the roof and 2 inches of insulation around all the walls and the slab and a window upgrade, which is definitely not going to be cheap in this project with all the other requirements. All right, thank you. That was it.
All right, fantastic, Ryan. Thank you. It feels like we just got the tortoise and the hare fable applied to ventilation and ERVs and flow rates. So really great stuff. I also was struck by the delta between the ventilation requirements that you showed with that Energy Star checklist and the PHIUS or PHI route. And I know that Beth has a question about that I think we'll start with in a moment. Really great questions. We do need to end at the top of the hour, so we'll try to get through as many of them as we can. But before we do that, we have let's hand it off to Kim for some events and some thank yous.
Great. Thank you, Zach, and thank you, Ryan. I just dropped some links in the chat for you all. We're going to start off with our podcast this week. I've pulled 3 episodes to share, 2 of which are from speakers at the upcoming Best of Retrofit conference on December 5th. We have Kara Haggerty-Wilson from Onion Flats and Andrea Michael from Love Shack Architecture joining us. We also have episode 12 of the Reimagine Edit. So if you are curious about the Reimagine Buildings Collective and some of the conversations that take place there, this is a really great place to start. So link in chat for you to check that out. Tomorrow we have a component spotlight event with Rockwool. They'll be joining us to speak about wildland urban interface fires in Canada and the US. And they'll be delivering some applicable solutions. So there's a link in chat there. And this is an event you do need to register for, so be sure to do so. Next week, we have a really exciting Accelerator Live episode continuing our Retrofit Month theme. This is an ambitious passive house feasibility study of a 1.3 million square foot GSA building in DC pursuing Enerfit level performance. So we'll be joined by Jonathan Stern from Cornerstone Real Estate Consulting and Matt Bowers from Oros Group. Hope to see you next Wednesday. And speaking of best of retrofit, this is our end of year celebration of the project's people and ideas transforming existing buildings into healthy, comfortable, and climate-friendly spaces for all. We hope to see you online with us December 5th. This is a 4-hour event. I'll be filled with real case studies, live Q&A with practitioners, and all sorts of solutions that you can put into your own practice. We're also submitting for AIA, PHIUS, and PHA credits. So if you're in that end of year scramble to get your credits sorted, we can help you out there. And one other note, we have added a 4th hour of the conference. This is all about healthy materials. We'll be joined by Joan Sarah Ruth from Parsons Healthy Materials Lab, and she will be speaking with Jacob Recusen as well as Chris Magwood. So it should be a really fun session, and more details in chat for you. A few little notes about the Reimagine Buildings Collective events. Most importantly, Ryan will be joining us on Friday. We have an hour set aside for your questions, so hopefully we'll see you at the AMA on Friday. We also have an event with Lindsay Shack next Tuesday. This is a fireside chat with Michael Ingui. And while I have the screen, I'm just going to thank our sponsors very quickly, and then we'll get over to Q&A. We'd like to thank our founding sponsors, 475 High Performance Building Supply, Ingui Architecture, Partel, Rockwool North America, and Zola Windows. Our champion sponsors include Bewiso, Cascadia Windows and Doors, European Architectural Supply, Facro, Intelligent Membranes, Icon Windows and Doors, LG Air Conditioning Technologies, and Source 2050. Our patron sponsors, Building Type, Brennan, Holzarm System, Innotech Windows and Doors, Lamelux, RDH Building Science, and Sanderson Sustainable Design. And finally, our stakeholder partner is NYSERDA, the New York State Energy Research Development Authority. So that was a lot. Thank you very much. Over to Q&A with Zach.
That was very efficient. I also want to mention, I see a lot of collective members here. The Best of Retrofit Conference, you have complimentary access as a member of the collective. So you don't need to register. Just you'll get a registration link from me and on the week of the conference. So just wanted to clarify. All right, so let's move to Beth.
Great, Ryan, thanks for the presentation. Hey, I'm trying to wrap my head around how these differences in ventilation recommendations between ASHRAE, Energy Star, I'm not quite sure if it's Energy Star or PHIUS, but like especially in multifamily where you typically have a resorc hood, and I believe that the required ventilation to meet PHIUS requirements is like 30 CFM for a kitchen. And this might, I know we have a short amount of time here, so we could also have this conversation probably over a drink sometime. But do you think that that's enough ventilation? I'm trying to wrap my head around different opinions from different sectors of the industry right now about this.
Yeah, I think it's a good question. I think it's pretty clear that exhausting kitchen hoods from the range directly outside is the best for indoor air quality. So we should start there, and also mention that Indoor Air Plus V2 that starts in January 1 for single family requires this as a strategy. So that. And when you do that with your range hood, you can reduce, the amount of continuous ventilation you have in your kitchen pretty significantly. That said, there's all these other impacts. So the real question is like 25 CFM or 30 CFM in a kitchen enough? Yeah, maybe. I think there's like, are there other mitigating factors? Like in a worst case scenario, can you open the window, right? I think that, yeah, that would be a question that I would also pose. Like, if you can't do that, maybe you want to preference more airflow. Yeah, and why? There's like another question, which is why like we have this Energy Star exception as passive buildings. And I don't really know exactly how that came up, besides there was some lobbying and they said, yeah, we can do this and it will work. So I've also heard that potentially in future versions of Energy Star that will be going away, right? And the trend is towards more ventilation rather than less. It's tricky. Like personally monitor my air quality, and I saw at like PHIUS+ some of the presentations on air quality in multifamily buildings that were really interesting. So I don't know, long story short, I think it's definitely a discussion to have with your engineer. And that's why I kind of put engineer versus CPHC, right? For me as a CPHC, I want that as low as possible because it makes the modeling, so much easier. The energy is so much easier, but we also have to be reasonable. And that's part of the reason I didn't push that multifamily down to 45, CFM, but left it at 60, which would be, 35 out of the kitchens, and 25 out of the bathroom for those small apartments, which I think is going to be fine.
Thanks.
Great. Thank you, Beth. And Richard, you're up next. Richard Gardner, you had a question about. Yeah, go
thank
ahead.
you.
Yep.
So yeah, Ryan, you really showed a good example where the SRE is impacting the space conditioning targets. And I'm faced in a similar situation, but my continuous ventilation is much higher, and it puts me on kind of the edge of the ERV family already. So going from, in fact, I'm planning on using the Renew Air EVL, and sizing up to the EV Premium X, doesn't really buy me anything.
Yeah.
And then, going up to a larger one puts me into the commercial ERV space, but then you can't, these are out of the scope of HVI, and you're on the manufacturing test data, which means a 12% derating. So then you're back into the same place. And then using two ERVs complicates the install and the balancing of that, especially if you were integrating the ERV into the tempered air into the return of the air handler. So I know it's a long question, but any guidance when you're on that edge of residential and commercial ERVs?
Yeah, so first, you're right. The Premium X and L, I think, has the same heat exchanger core. So the only difference is the fan in it, which is something maybe that's very specific to that, but useful to know overall. Like, you just really want to look at the kind of specs. So it will push more air, but you're not going to see really any benefits because the size of the core is the same or very similar. With the other question, like, is it one ERV or two, or like, how are you ducting it and all these sorts of things? I think you can get away with the 12% derating if you are following the right specifications. So I would, and I believe that's a PHIUS rule. So I would ask PHIUS about that, on whether, or if you can get the right data that would not require you to derate the efficiency, and I think you probably can. The other thing is, like, the two ERVs, sometimes that's actually a kind of an okay thing even from an install perspective. Like, on some of these large houses I'm working on, there's one right now where there's two separate mechanical room spaces. There's actually two separate water heaters, and they went with one ERV. And that decision meant that there was a lot of extra ductwork. Granted, less penetrations to the outside, but that ERV is having a lot of trouble getting balanced across those really long duct runs. And two smaller or similar sized systems, one on each side of the project, would have actually reduced the amount of ductwork, I think, pretty significantly in that particular project. So it is about the layout and the project and where this is gonna work. The other thing to mention is, I kind of know where you are in the country, and you don't have the same temperature difference as some of these really cold climates, and you're going to see this SRE matter a lot more when the temperatures are extreme. So you're kind of getting, yeah, maybe not as much benefit as someone in the really northern part of the country would too.
Yeah, if you recall, when we did the consulting together, we talked about this same problem, right? Now I'm getting close to the actual install and still struggling with an answer on how to implement and install this.
Yeah.
Thank you.
All right. Thank you, Richard. And George Nuggles, you have a question. Looks like you're here, George.
Thank you.
Yep.
I I appreciate what you were saying about using the larger model with a higher capacity. Are you also putting in ducts that have that same capacity, or are you putting in ducts that have the lower capacity? And then what are the implications for filter replacement, dust accumulation in the duct, and cleaning when it comes to your cost model?
Yeah, so I think this is a kind of it depends question. In most of cases, the ductwork won't need to change very much. We're reducing the flow rate in many cases, but even if you have like are kind of needing to size up for mass or max capacity, let's say of a unit, I think the reality is it won't change a lot. I mean, I have some projects that are maybe using 8-inch or 7-inch ducts instead of 6, for example. That could change on the much larger centralized projects, but the ones we were really looking at today were decentralized with many smaller ERVs. So I don't see the ducts as being much difference. Now, the fan or filters are definitely something to consider, and I think that's the biggest downside of using multiple ERVs is you have a lot more maintenance and you do have those additional filters. I'm also not sure that the size of the filter matters that much. I'm sure like the bigger ones are maybe a couple dollars more or something, but I think it's more the quantity of them that would come into play there. I don't know. There was a couple other questions maybe in there. If
That'll do. I don't want to take too much time.
Okay. Thank you, George. We are over time, but we're going to squeeze in one more question from Carmel. I think this is a question probably it's on a lot of people's minds when you mentioned bringing the ERV outside the envelope. So Carmel, please fire away.
Thanks. Yeah, and I don't know if this is going to get answered here, but it's more my curiosity, right, between rated efficiency and actual efficiency of what happens to those units when they're operating at a low ambient temperature outside versus a constant ambient temperature inside.
Yeah, and I don't know either, so it won't get answered. But I saw that in the chat and was like, yeah, it's a good question. There's a couple other things that happen too when you pull these outside, especially if you're using like roof mounted units, like the ducts get very short. The duct between, the unit and the thermal envelope. If it's in a mechanical room, you have to duct from the outside to the thermal envelope, and those duct losses are counted in the model. But when it's roof mounted, you can get that to be very short, sometimes like a foot. And so that also has this like outsized benefit that I'm not 100% sure if it's like totally real, because the space inside that ERV is also, subject to whatever that outdoor temperature is. So, I think it's a good question of what that real performance is. But modeling can look a lot better on any project that's cooling or cooling load challenged for sure.
Thanks for squeezing that in.
Yep.
Yeah. Thanks, Carmel. Ryan, thank you so much. This has really been awesome. I'm sorry for folks who didn't get their question answered. Please consider joining us on Friday in the collective at noon Eastern, because we'll have a whole hour of questions and answers with Ryan, and you can dive into anything ERV, HRV, building science, passive house practice related. But a big thank you, Ryan. I don't know if there are any final words you'd like to share with us before we close up.
No, it was great to be here, and yeah, I'll see some of you maybe on Friday.
Awesome. Thanks, everybody. Have a great rest of your week.